This is a presentation of our 2022 Senior Capstone project entitled Zero Trust Architecture on Internet of Things Networks by Alexander Carr
and Emma Mirabelli. Internet of Things devices have become increasingly common in many households. Due to the wide range of device types and multitudes of data being relayed over a network, there is no standard level of security for IoT devices. A zero trust architecture is an advanced security tactic that removes the assumption of trust given to devices and continually verifies and authenticates devices in a network. Implementing a ZTA on a network of IoT devices increases the security of the network and ensures safe data transfer between devices. The outcome of this project is a fully functioning, secure network of IoT devices connected over Wi-Fi and a web interface displaying data and statistics. All devices in the network are verified upon registration and transaction using multi-factor authentication. The initial plan supported both MQTT and CoAP communication protocols. However, after extensive implementation testing, we concluded that CoAP does not currently support the encryption functionality needed to be secure. Therefore, all data is transmitted through SSL encrypted MQTT. So here you can see one of the IoT educational kits that are used as the IoT clients in the network. You can see that there are multiple sensors on the board. We used two in particular. The first one is the analog temperature sensor, and the second one is the digital pressure sensor. And here you can see all of the wiring connected.
We also use a Raspberry Pi 4 Model B to host the server, MQTT broker, and web interface. We connect it to the network using the Ethernet port located on the side, and this Raspberry Pi is able to receive all of the MQTT messages on the network from the IoT clients. Here is a full demonstration of our MQTT broker, server, web interface, and some clients in action. First, we need to start out by running our MQTT broker, which is run using Mosquito. Next, we will launch our server, which is run using Python, and this is going to prompt us for our MQTT username and password for security reasons, and then it is also going to ask us for our database password because the database is encrypted and will require a password to be accessed. As you can see, the server is successfully started up and is now ready to receive MQTT connections. Next, we will start up our web interface, which is run using Python Flask. After running, it can then be accessed in a web browser. Next, we will start up our two clients. First, the client is run using our MQTT client file with the IP of the MQTT broker. In addition, when you start up the client, it is going to prompt the user for MQTT username and password, which is required for security reasons. In addition, when the client first starts running, it's going to register the device with the MQTT broker, which involves exchanging certificates and recording some client information. Once the client is registered, it can successfully send messages to the broker, which are then relayed to the server. As you can see here, when we move and refresh the page for our web interface, we now have live updating security statistics and temperature and pressure data from IoT clients. So when the IPs of the two clients are entered into the two temperature and pressure charts, these charts will update with live information that is being relayed to the server from the clients. In addition, we also have messages statistics, IoT devices statistics, and statistics on the MQTT broker. All of these statistics show sent messages and received messages in addition to the number of IoT devices connected and registered, and also the status of the MQTT broker with how many topics it has available.
To evaluate the security of the zero trust architecture, we ran a couple of tests. The first test is a man-in-the-middle attack using Wireshark, in which the data packets are intercepted and tried to be read. So as you can see, the command being run is to grab one packet coming from the IP address of one of the IoT clients. So there's the source address, and the destination address is the IP of the MQTT broker on the port 8883. Then as you can see, this is the data in the packet, but it is encrypted, so it's unable to be read.
Our second test is a bad actor test, which simulates someone who has the correct login information, but not the correct certificates needed for SSL encryption and verification. We first start out this test by launching our MQTT broker, and then we are going to use a Mosquito subscription client, which has the admin login information to log in and connect to the MQTT broker. However, in this case, we are using certificates that are bad and should not be verified with the MQTT broker. And so when we run this program that tries to subscribe to the data/temperature topic, what will happen is a TLS error will occur. This means that the subscription from the client was rejected. And so as you can see here on the MQTT broker, a client tried to connect on port 8883. However, there is an SSL error with decryption, which means that the certificates used were not correct. Therefore, the client was disconnected and an error was made.
This concludes the presentation for our project. Thank you for listening.